Okay, so please be seated. Yeah. Okay, so welcome back. The next lecture we have from Professor Chong Wang from the Perimeter Institute of Theoretical Physics in Canada. He's an expert in topological phases of matter, quantum spin liquids, quantum Hall effects, quantum phases transitions, etc. So he will be telling us about a web of duality in 2+1D.
Thanks. Yeah, so as you can see, I'll be telling you a story that by now has been there for a while. And for those of you who know this story before, I'll try to still keep you somewhat entertained by making a few remarks that are not necessarily new results per se, but are things that are interesting and important, but haven't been emphasized very much in the past. Also, as you can see that for some reason, for all my collaborators here, their profile pictures are all tilted toward one particular direction. So maybe I should give this talk like this. Yeah. So, okay. So I want to talk about field theory IR dualities. So broadly speaking, I want to talk about situations where I have some well-defined field theory. Typically, in the UV, there are some free theories, and such that the two theories are not the same in the UV. I mean, there are typically free theories in the UV, so that's very easy to check. But thanks to the magic of renormalization group flow, they flow to the same IR physics, right? And whenever this happens, it's nice for two reasons. One is that this may be useful, right? Maybe some questions that's very difficult to ask to answer in theory one is fairly easy to figure out in theory two. The worst case scenario is you understand neither theory, but at least you manage to reduce the number of unsolved problems by a factor of 2. Also, it's just intrinsically satisfying. It's pretty cool that when this happens. Let me give you a canonical example that's very well known in condensed matter literature. It's a non-trivial example in 2+1 dimension involving strongly interacting theories and no supersymmetry. Right? So it's a story that's been known since the late 70s, early 80s. It's known as the boson vortex duality in 2+1 dimension or 3D. So on the left side is basically a 5-4 complex scalar. So in the UV, it's just a Gaussian theory that in 3D flows to the non-trivial O2 Wilson-Fisher fixed point. It's a non-trivial CFT. So on the right-hand side, this is known as a Abelian-Higgs theory. So you have again a 5-4 complex scalar theory, but now coupled to a dynamical U1 gauge field little a. Oh, by the way, in this talk, this capital A typically means background gauge field. So it's just a number that I put in that couples the theory that I use to probe the theory. So, but little a typically means a dynamical gauge field. So it's something that you need to integrate over in the plot integrate. It's really frustrating. And so you couple this 5-4 theory to a U1 gauge field with a Maxwell term. And the U1 gauge, and now the background gauge field is coupled through the mutual Chen-Simons coupling to the U1 gauge field, to the dynamical U1 gauge field. Yes. Now the claim is that if I start from in the UV, start from the free theory, right? Free scalar and free photon, and I first turn on the 5-4 interaction. So I let the scalar flow to a Wilson-Fisher fixed point first. And then I turn on the gauge coupling. Then in the deep IR, this theory also flow to the O2 Wilson-Fisher fixed point. Right? Oh, by the way, if you have a question at any point, just feel free to interrupt. Right? And this has been proposed mainly based on lattice constructions by Peskin and subsequently by Dasgupta and Halpern. And it was only numerically verified much later in these papers. I should say that this procedure of first flowing to Wilson-Fisher and then couple the gauge field and eventually flow to Wilson-Fisher. First flow to the Wilson-Fisher of the Higgs scalar and then eventually flow to the real Wilson-Fisher. Practically, what that means is that when I write down the Lagrangian, this 5-4 coupling constant is larger, much larger than the gauge coupling E squared. Okay? If I'm in the opposite regime, then in fact I get a first order transition. So this order actually matters. By the way, in case you're not familiar with 3D gauge theories, both this 5-4 coupling lambda and the gauge coupling E squared has the dimension of energy. Right? So this is very different from 4D where everything is marginal. So they naturally sets your RG flow scale. So IR really means I'm flowing to momentum scale that's much smaller than all these dimensionful quantities. So this statement is actually, as far as I can tell, there's no analytic way to actually derive it. Partly because both theories flow to strong coupling in the IR, and there's no analytic solution to either of those. So as I said, if you really want to be sure about this duality, you need to do very serious numerical check. Right? So I don't know how to do that, but at least we can do something much more naive. Right? At least we can check that this statement of the duality makes sense. Right? It's not obviously wrong. So there, essentially, but by saying that, what I mean is you can check all the kinematic aspects, right? Symmetries, like what happens with mass deformation. Do you get the same phase diagram? You can check all those things, and those things are very easy to check. For one, both theories have a global U1 symmetry. So in the 5-4 Wilson-Fisher theory, you have the conserved, essentially particle number conservation. And on the gauge theory side, the corresponding conserved current is just the gauge flux. Right? So this guy is naturally conserved. The continuity equation is satisfied trivially. So what that means is conserved boson charge actually correspond to conserved gauge flux. And that's the reason why this is called the boson vortex duality, because that tells you that the original boson phi and this Higgs scalar, this dual boson, they actually see each other as 2 pi flux. So you should interpret this Higgs scalar phi as the vortex of this original boson, capital phi. Okay. And then you can look at local operators. By local, I mean local and gauge invariant operators that's charged under this global U1. So on the Wilson-Fisher side, it's just your 5-4 scalar. On the Higgs theory side, you have to work a little bit to realize that this is a local operator that's charged under the flux U1 symmetry, and that by definition, I mean it's an operator that creates flux basically. Right? This normalization means that it's an operator that creates flux 2 pi, which by definition is a monopole or instanton operator, the 3D gauge. Right? So the statement is that these two operators do each other. Okay. So that's a check in terms of symmetry and local operator content. So you can do a little bit more by checking what's called the phase diagram. So essentially, you make some mass deformation, right? Some relevant deformation on both theory and check that both theories should flow to the same thing, right? At least that one. So you can turn. So here the obvious thing to check is turning on a scalar mass. It turns out if I turn on a positive mass on the left side, well, you get the scalar got gapped, so the vacuum is trivial. Right? It's a unique symmetric vacuum. And on the gauge theory side, it turns out what you should do is to turn on the opposite mass, the negative mass for the Higgs scalar. This way, the Higgs field will condense, but then the gauge field will be gapped. right? So and then also you get a trivial vacuum. It's no degeneracy, no spontaneous symmetry breaking. The opposite limit is when you have a negative mass on the O2 Wilson-Fisher side. So there you just get a superfluid or XY magnet, where the vacuum is no longer trivial because you have the Goldstone boson. And on the Higgs side, you have, again, you turn on the opposite mass, which now means a positive mass. So this Higgs scalar is now gapped. In the IR, you just get a free scalar. Sorry, a free photon. And it's an interesting fact. It's an interesting but straightforward fact that in 2+1 dimension, a free photon is pretty much the same as a free Goldstone boson. Simple check is photon in 3D has only one polarization. So in case this is not very familiar to you, there is a analog in 1 dimension lower that's hopefully much more familiar. It's just 2D Ising model, right? So if I think about 2D Ising model, let me just tentatively write it as a real 5-4 scalar theory in 1+1 dimension. I can also think about coupling the scalar to a background Z2 gauge field. Now this dB is really just a schematic way of denoting that I'm coupling the theory to a Z2 background gauge field. In the simplest case, what this Z2 gauge field does is to tell you whether my scalar has periodic or anti-periodic boundary condition along various cycles. And this 2D Ising model has a famous Kramers-Wannier duality, if you like, the low temperature, high temperature duality that exchanges the ordered and disordered phases. So in a similar language, that duality can be expressed in this fashion. So essentially, I'm now having a dual real scalar, which is basically the domain wall of your Ising model in 1+1 dimension. That's now coupled to a dynamical U1 gauge field. Now let me call it little b. By dynamical Z2 gauge field, what I mean is when you do path integral, you sum over different boundary conditions. Right? That's what dynamical gauge field means. And you turn on the opposite mass deformation. The fact that this two mass come with opposite sign is just the fact that the order and disorder phases got exchanged under this Kramers-Wannier duality, right? And finally, you have this term. This is B cup product with the background gauge field capital B. What physically it does is to assign a Z2 charge of this global Z2 symmetry to a flux of little b. If I think about an event where the boundary condition of my dual scalar changes from periodic to antiperiodic, for example, that event carries a global Z2 charge. Right? This is what happens in this Kramers-Wannier duality. This is really just saying that I'm exchanging my spin and domain walls in an Ising model. So this is very similar to how this little a d capital A works in the particle vortex duality. I'm assigning global symmetry charge to some gauge flux. And again, the original Ising scalar phi in the dual picture is just a flux insertion operator or an instanton, if you like. That's very much similar to the monopole operator. Right? So again, this 3D story is very much in parallel to the 2D story. Yeah, that's the thing. Discrete gauge field tend to have fairly trivial dynamics, and that's why this is actually simple. Yes. Sorry. Oh, Um, no. The gauge theory side, I think what you end up simulating is an R gauge theory. Right. Yeah. 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 That's not a gauge theory. Right. In the IR there's an effective gauge theory, but in the UV it's not. Right. The part of the difficulty of verifying the duality is know that you are honestly simulating something that in the continuum you want to call a gauge theory. Yeah. Okay. Yeah. Yeah. So dynamically it doesn't do much. Topologically it's doing a lot, but dynamically it's fine. Yeah, what they actually verified is that the critical exponent you get is the same as XY models. Um, right. Okay. So that's that's known stuff. It's been known for decades. And here's an example that wasn't as familiar at least 10 years ago. So this is an example that instead of involving bosons on both sides, involves fermion on one side. So this is a fermion boson duality. Sometimes people call it the 3D bosonization. It's a somewhat confusing terminology, but let me also use that terminology. So here's the statement. Now this is a much simpler field theory, actually, just a free Dirac fermion, a free two-component Dirac fermion in 3 dimension, in 2+1 dimension. Um, and the statement is that now this is also due to a abelian Higgs theory. A Higgs field phi, a complex scalar, now coupled to a dynamical gauge field little b. It's almost the same as in the previous duality. The only exception, the only difference is that now you have an additional Chen-Simons term in your action. Right? This little b, little b. Right? It turns out that this Chen-Simons term changes pretty much everything. But before I go to more detail, let me just clarify a little bit what I mean by this, because in the literature, different people tend to use different notation. And so when I write this, the Dirac fermion really means a Dirac fermion regularized in the polyvelar, polyvelar regularized. Right? So the partition function looks like this. In particular, the phase factor is given by the eta invariance, which in the language of Hall conductivity, it gives you Hall conductance -1/2 times the natural unit. So sometimes, just to avoid confusion in the literature, it's denoted as Dirac fermion with polyvelar regularized with a particular sign choice. Now the important thing is that this Dirac fermion defined this way is fully gauge invariant under U1. There's no issue with gauge invariance. You can promote the gauge field to dynamical one. There's no problem with that. But under time reversal, it's almost time reversal invariant, except there will be an additional Chen-Simons term at level 1 that appears under time reversal. Right? So strictly speaking, it's not time reversal invariant because your Hall conductance changes. And this is the famous statement of parity anomaly for the Dirac fermion. All right, so now let's go through the previous exercise again. By the way, this one has not been checked numerically as seriously as the boson vortex duality, because obviously trying to simulate this is going to cause you a huge pain. You need to overcome the sign problem. But at least we can do the simple thing as we did for the boson vortex duality. There's obviously a U1 symmetry with charged local operator, which is just your free Dirac fermion. So you can check that on the dual side. So again, you're talking, whenever we're talking about a U1 gauge theory in 3 dimension, there is naturally a conserved global U1 charge, which is just the gauge flux. And the local operator that's charged under this U1 global symmetry is naturally some monopole operator. Now, the only difference caused by this Chern-Simons term is that the bare monopole is not gauge invariant, formally speaking. So what you should do is to attach a Higgs scalar, which also carries gauge charge, and the combination of this combined object turns out to be fully gauge invariant. So it's a legal local operator. You can talk about that. And this is really you can think of this as a relativistic version of flux attachment, right? So you start with a monopole operator, which looks like a boson. You have a scalar field, which looks like a boson, but the combination, when you combine the boson and this flux or this vortex, because of this Chern-Simons coupling, this combined object becomes a fermion, which is nothing but your free Dirac fermion. Okay. So at least that kinematic aspect checks out. So you can check the phase diagram. It's fairly, it's also fairly straightforward. So so you can deform the Dirac fermion with a mass term, right? And with either sign of the mass, the vacuum is unique, right? Because you just get a gap fermion, so you can integrate it out, and then your vacuum looks boring except for your response term, right? You may get a turns out if with the previous polyvelar regularization of the Dirac fermion, it turns out for negative mass you get a Chern-Simons term at level -1, and for positive mass you get a completely trivial vacuum. You don't even get a Chern-Simons term. Okay, so what you end up getting is at this critical point is basically an integer quantum Hall phase transition. So you can do the same, play the same game on the abelian Higgs side. So turns out with you deform the scalar theory with a mass term like this, then with one sign of the mass, say positive, if phi is positive, you get a massive theory, right? And then you just integrate out the scalar field. You end up with a pure U1 Chern-Simons theory at level 1. Turns out that's a trivial topological quantum field theory. So U1 level 1 is a trivial QFT. So you can integrate out this U1 gauge field, and everything is quadratic. So integrating out really just means solve the theory classically. Right? Just solve the classical equation of motion, put it back in. Then you just get a response term of the background gauge field, right? Which agrees with this one. And with the opposite mass, the scalar field phi condenses. Once phi condenses, the gauge field is Higgs. Doesn't matter what the Chern-Simons level is, you get a trivial vacuum. So that phase diagram also agrees. Okay. So phase diagram checks out. Okay. There is a slightly more non-trivial check to this duality. In fact, this is the check that was so non-trivial that this was the first evidence that convinced me that maybe this is really true. Right? Maybe this duality really works. When you think about time reversal symmetry, so as I mentioned, the free Dirac fermion in 2+1 dimension has a time reversal symmetry. Okay, it has a de Hooft anomaly. There's a parity anomaly, but fine, it's still a symmetry, right? So the Dirac fermion is invariant up to this ADA term under time reversal. And then you can ask, well, what happens to the right-hand side, right? The issue is that whenever you have a self-Chern-Simons term like this, BDB, naively, it's not time reversal like that. So if you apply a naive time reversal operation, well, you see that this BDB changes sign. So what do you do? Well, it turns out, so let me not go through the detailed algebra. It's actually just a few lines of algebra. But it turns out this theory you get after time reversal symmetry is actually dual to this theory in the sense that this phi tilde is now the vortex of the original phi. Right? So time reversal is implemented on this Higgs scalar phi, as a boson vortex duality, the same boson vortex duality I was mentioning at the beginning, right? Once you do that, you realize that the theory is actually compatible with time reversal symmetry. So there is actually a very nice cartoon picture for that, right? So remember, I interpreted this this Dirac fermion as a combination of boson and vortex in this duality. It turns out, the Dirac fermion comes with a spin, right? And the spin is it's spin hot. So if you do time reversal twice, you get a minus sign. It turns out that spin can be interpreted as essentially the dipole moment between this boson and the vortex, right? So now under time reversal, the boson and vortex exchange with each other. So boson becomes vortex, vortex becomes the vortex of vortex, which is the origin boson. So under time reversal, this dipole moment flips direction. If you do it twice, you are performing essentially a braiding between the vortex and the charge, and because of the Chern-Simons term, that gives you a minus sign. So things work out in a somewhat non-trivial way. And by the way, this, even though I'm drawing it as a picture, you can literally see this happening on some lattice regularized version of this duality. Right? So even time reversal symmetry works out in a somewhat non-trivial way. Okay, so those are all like consistency checks. Some of them pretty non-trivial consistency checks, but none of this serves as a proof of the duality. There are a few more consistency checks you can do, which has been done by various people over the years. As I said, there is no Monte Carlo data on this, on the abelian-Higgs theory because of the sign problem. There is one recent development which I want to mention, done by Shai Chester and Will Chekak-Krampa and his student Dubius. So essentially, what this people have done is to calculate in some large n limit the scaling dimension of the monopole operators in this abelian-Higgs and Simons theory, and then do commit a crime which many of us in the community always commit, which is at the end of the day set n equal to 1. You compute like the leading order and subleading order, and for a reason we still don't fully understand, if you do that and put n equal to 1, we only have one flavor. So sorry, n is the number of flavors of the Higgs scalar. So when you do that extrapolation, the numbers you get seem to be suspiciously close to the numbers you expect from free Dirac theory, right? So the error is within 1%. And that works for a subset of these monopole operators, which are I think unique scalars, Lorentz scalar. So as I said, we don't understand why it's supposed to work so well, but the fact that there are so many numbers that numerologically works out so well, it probably means something. So that's one of the late development. Yeah, so that's the status of this duality. It makes a lot of sense. It's likely that it's right. We don't have a completely rigorous proof, or like, we don't have any proof yet, but it's very likely to be true. Okay, so again, just like the boson vortex duality, which is you can view it as an analog of the Ising high temperature, low temperature duality. This 3D bosonization also has a 2D analog. So here's the 2D analog. So it's basically the Jordan-Wigner duality, right? So the statement is that if I look at a 2D Majorana fermion, it's well known that it's also dual to the Ising model, right? The Ising CFT. Now the more precise statement, one way to make that statement a little bit more precise, is the following. Here's your 2D Majorana fermion. So now this chi is a real fermion. The statement is that this theory is dual to this guy. So phi is again a real scalar. It's basically the Ising model. And well, that it cannot literally be due to the Ising model because this theory is a fermion theory. It has fermion, and all that Ising model doesn't have that. The way to fix this is to couple this Ising model to a dynamical gauge field, dynamical Z2 gauge field little b. So you are summing over periodic anti-periodic boundary condition in your path integral. Again, the global charge, this fermion parity, this fermion Z2 charge is now carried by the Z2 instanton of your Z2 gauge field, which is very similar to the Kramers-Wannier duality, except now you also have this additional Z2 topological term involving the dynamical Z2 gauge field. This is a Z2 invariant of this gauge field known as the R invariant. It plays the same role as the Chen-Simons term BDB in the previous 3D bosonization, in the sense that if you trace down what this term does, is that this term, what this term does actually is to attach this phi, this real scalar, this Z2 gauge charge, to a flux or instanton operator of the Z2 gauge field, and converting it to a fermion. Right? So it does pretty much the same thing as what a Chen-Simons term does to a monopole in 3D. So the right hand side, it only appears to be like a boson theory. It doesn't explicitly have a fermion, but because of this flux attachment, the local operator, which is a flux insertion operator of your dynamical Z2 gauge field, actually becomes fermionic. That's how this duality can really make sense. Right? And also, if I think about the chiral symmetry of this 2D free Majorana fermion, right? This theory has a Z2 chiral symmetry. It turns out the chiral symmetry is implemented on the dual theory, again, as a Kramers-Wannier duality on this phi. Essentially, under the chiral symmetry, this Ising scalar phi exchanges, becomes its domain wall, vice versa. So that's very similar to how time reversal works for the 3D bosonization. You see that it's pretty parallel structure, except for the 2D one, it's actually very familiar things. Okay, so that's one of the 3D duality. That's as I said, it's most likely to be true. And what we and others have realized is that now you can start from one duality and try to come up with many others, or essentially infinitely many others. So you can start from a duality statement like this, right? Theory 1 is dual to theory 2. Both theories have a U1 global symmetry, so you can couple that to a background U1 gauge field. And then there are two operations you can do. So one operation, which is sometimes called T, is that you just add a Chen-Simons term to both sides, right? By the way, I'm assuming that doesn't hurt. I'm assuming that both theories are fully gauge invariant. No anomaly with involving the U1 and so on. Also, this task of adding a Chen-Simons term with integer coefficient is also fully gauge invariant. Everything is completely legal. And then there's the more non-trivial operation, which is called S, is essentially to gauge this U1 symmetry, right? So what you do is you take this theory and you promote this background gauge field to a dynamical gauge field, which means you are summing over the gauge field in your path integral. And in that process, you are also, you eliminate a global U1 symmetry because you've gauged it. But the nice thing about 3D is that you also get back a global U1 symmetry because of the conservation of the gauge flux. Right? So in this way, you get another duality that takes this form. And then you can keep doing this sort of thing. You can perform an S and then perform a T and another T and then an S. Keep doing that. This way you generate actually infinitely many more dualities. Sorry? Sorry? Yeah. This is a little a. Yeah, sorry. That was a typo. Yeah. Actually, let me make a remark about some subtlety in this procedure. One thing we often do, or something like this is what we often do is consider performing this S operation twice. Okay? So if we do it very carefully, let's do it very carefully. This is a rare occasion where I want to do things a little bit carefully. So okay, suppose I perform S once. What does that mean? Well, I have my theory coupled to gauge field, and I gauge my theory. Well, if I really want to make things really well defined, I better do it in such a way that while introducing a Maxwell term with some gauge coupling square, right? And then I let the archie flow take me to the fixed point, which practically means that I take E squared to be large, right? Much larger than my probing energy scale. And of course, there's a mutual coupling to the background gauge field, ADB. And then I promote this B to a dynamic gauge field, which also means that I should add a Maxwell term for little b. Right? And then eventually this little b couples to the background gauge field. But the fact that I'm introducing little a first, let it flow to the IR, and then couple to little b, means that I should set up things so that E1 square is much larger than E2 square. That's what I mean by first introducing little a and then introducing little b. However, if I assume that this order doesn't matter, right? So if I assume that I can deform this theory to the point where it's actually it's opposite limit. I have E1 square much smaller than E2 square. Then I can do some simplification, right? Because if E2 square dominates, then I can just I can just drop this Maxwell term. Essentially, this thing becomes a Lagrange multiplier. Little b just couples to linear order, and then I can integrate out little b and set little a equal to minus capital A. Right. Once I set little a equal to capital A, I eliminate all the b's, and then it becomes just L capital A. Right. 2 minutes? Oh, I thought I started. Yeah. So very good. The point is the path integral of little b can be done anyway. If you do that, what you get is a Higgs term, is a mass term for little a with a mass E2 square. And if E2 square is much less than E1 square anyway, we don't know the effect of that mass term. Right? It's only when E2 square is much larger than E1 square, we know the effect of that mass term is to set little a to just 0 or minus capital A. Yeah, that's the more precise way of saying it. Yeah. Right. So once you make that assumption, then you get the conclusion that doing S square is basically doing nothing. Well, okay, there is a charge conjugation because you're going from capital A to minus capital A, but in all these theories, we consider charge conjugation is pretty boring, so let's not worry too much about it. So you have S square equal to 1, essentially. And similarly, you can perform a similar series of tricks to check that ST cube equal to 1. So SNT really generates an SL2Z modular. So this operations on this dualities essentially generates SL2Z sequence of dualities. Only if we assume that these two limits can be exchanged, right? Which is an assumption that normally we have no idea how to really justify. So that's a subtlety that most of the time we don't worry about, but occasionally we may want to keep in mind, because that means even if one of the duality is true, if for some reason this two limits cannot be exchanged, then the other dualities may not be true. So a little bit more remark on SL2Z. So in fact, not only you generate more dualities, the duality itself can be formulated as some statement about SL2Z, right? So typically all these dualities we end up saying is some abstract level is saying that theory 1 is dual to theory 2 after some SL2Z operations. Right? For example, the boson-vortex duality is saying that the Wilson-Fisher boson is dual to Wilson-Fisher acted on by S, right? Because S is just gauging the U1 symmetry. And this 3D bosonization is saying that the Dirac fermion is basically Wilson-Fisher. You first perform a T, which is adding a Chern-Simons term, and then performing S, which is gauging the U1. So all these duality end up being pretty compact expressions like this. So there is another thing of another context where this SL2Z appears very naturally. Recall that in 4D, right, 3 plus 1D U1 Maxwell gauge theory, right? There is a set of electric magnetic dualities generated by SL2Z, right? So formally the way to think about this is you can express the gauge coupling in this way. So the imaginary part is basically your fine structure constant, inverse of that. And the real part is your theta angle divided by 2 pi. And if I think about exchanging EM, charge and monopole, for example, turns out what that does on this coupling constant is to set tau goes to minus 1 over tau. So the modular transform. And the T transform, which sets tau to tau plus 1, is just nothing but shifting theta by 2 pi. Right? You've just seen the discussion on this before. Okay. So it turns out these two SL2Zs are very much very deeply related. It turns out if you combine these two stories, what that gives you is a EM duality, essentially a bunch of SL2Z duality of U1 Maxwell theory, but with boundary, with some critical theory on the boundary. So in particular, what I mean is this. So suppose this dual theories we consider they don't live just purely in 2 plus 1 dimension, but instead they live on the boundary of some 4D bulk, right? And suppose I have a dynamical gauge field, essentially photon that lives in the 4D bulk, but also couples on to this boundary degree of freedom. So now this capital A's are dynamical gauge field, but they also link to the 4D bulk. So if I have a duality, I can also couple the dual theory to the same bulk Maxwell theory like this. It turns out it takes a few lines to derive this fact. It's derived in our paper. If you're curious, you can take a look. But it turns out you can perform this SL2Z operations on both sides and generate some neat statement. For example, you can essentially perform an inverse SL2Z operation on the right-hand side. It turns out performing SL2Z on the boundary theory in the sense I discussed, right? S means gauging the U1, T means shifting the Chern-Simons level, is equivalent to can be done or is equivalent to performing an SL2Z electric magnetic duality in the bulk. Okay, so what you end up getting is that theory 1 is now dual to theory 2, but the bulk coupling are changed, right? So this bulk coupling becomes the original tau, but now shifted by this SL2Z, the inverse SL2Z operation, right? So the example here is that a Maxwell theory with a boundary Dirac fermion is dual to another Maxwell theory with a boundary Wilson-Fisher, but now with the gauge coupling shifted this way. This is just how I define my theory. I'm just imagining putting A in the bulk. Oh yeah. You can just live on the surface, but I'm just thinking about a situation where it lives both on the surface and in the bulk. No, it's not needed. It's not needed. Yeah, you can just choose to consider this theory. No. Capital A is dynamical. That's the thing. It's dynamical. Oh, sorry. Yeah. It becomes dynamical, and in the bulk, it actually you should have the bulk Maxwell term, and the bulk Maxwell term comes with the coupling constant tau. That's what I mean. Yeah. That I should have used little a, but I also want to emphasize the fact that little a also leads to the bulk. It's not a 2 plus 1D gauge field. The gauge field is a 2 plus 1D. Yeah. Sorry. Yes. Yeah. Yeah, but everything has gauge charge. Yeah. Because in the bulk, your among your charge monopole and dion, something will be fermion. If you make your charge and monopole boson, the dion will be fermionic. So something will be fermionic anyway. Sorry? No. I mean, you can okay. In this pure setting, this boundary fields do not lead to the bulk. But if you imagine that they are you can leak to the bulk, but just comes with a gap, with a mass gap, then they will correspond to either charge or monopole in the bulk. Yeah, that's what I mean. Oh, no. It's not a symmetry. It's not a symmetry, right? I'm not. You can choose. This tau goes to some tau prime, right? Like this. Yeah. That's true. So um, part of that is taken care by by carefully demanding, some of them is ordinary U1, some of them is spin C. At least part of them is taken care. I'm not sure about the full ZA. Yeah. Yeah. For example, in this theory, it's actually a spin C gauge field. This theory is ordinary U1. Yeah, but I need to think about the full ZA. Good question. Okay, so just as an entertaining fact, you can keep comparing to the 3D to the 2D story. Okay, you don't get that much new stuff, but it's entertaining and also reassuring that we're not doing something totally crazy. As I mentioned, this the role of the complex 5-4 boson, I mean the Wilson-Fisher boson and Dirac fermion is somewhat parallel to Ising scalar and Majorana fermion in 2D with U1 gauge field and global symmetry parallel to Z2 gauge field and global symmetry. That's how you compare boson vortex duality to Thomas Wannier. You compare 3D bosonization to Jordan Wigner. the way that happens is that mutual Chern-Simons term, which does flux attachment, is very similar to this discrete A cup B term. And the self-Chern-Simons term, which does the statistics transmutation, converting boson to fermion, is very similar. It's very much in parallel to what the arc invariant does to the 2D theory. You can play a very similar game of thinking about SL2Z operation. It turns out what you can do in 2D is much less. It's SL2Z2. So this is a finite group. So you don't get to generate infinitely many cool stuff, but some finite number of those. And this this SL2Z operation has the simple has a funny connection to the EM dualities in 4D U1 gauge theory, while it's also a very well-known fact that this dualities involving 2D Ising or Majorana fermion has a deep connection to the 3D Z2 gauge theory or the Z2 topological order. So things are very much quite deeply in parallel. How am I doing in time? Okay. Okay. I can finish early. In fact, yeah. So just mention one fun fact is that if I, as I mentioned, you actually through this SL2Z operation, you actually get to generate infinitely many dualities in 3D. And here's one that's particularly fun. I'm writing it actually in a somewhat illegal way but in case you're an expert, this looks somewhat illegal. Don't worry, we do have the legal version, fully legal version, lawyer approved in our paper. But I'm just writing it in such a way that it looks entertaining, because it's just a statement that a free Dirac fermion is dual to a Dirac fermion coupled to U1 gauge field. That's it, nothing, right? So that looks short. This equation looks short and nice, right? And it's very much the fermionic analog of this well-known boson vortex duality, right? Except now the particle is a fermion, and the vortex, which is the gauge charge, is also a Dirac fermion. Right? In some sense, this, if I ask you to write down the simplest possible quantum field theory in 2+1 dimension, these are probably the simplest you can write down. And it's nice that they happen to be pretty much the same field theory. And this particular duality is also related to many things in condensed matter physics. It's related to the story of half-field lambda level infraction quantum Hall effect, and the story of topological insulators and superconductors, which a lot of us have had much fun working on actually 10 years ago. Okay, so that's pretty much it. In fact, this duality story is yeah. No, that's because of this finiteness of this guy. You don't get that. In fact, you try to do the same thing. I think for this one, you do something like ST square S, but that guy is manifestly trivial in SL2Z2. Yeah, you don't get that. Okay. Right. So the turns out that this duality story is related to many things I didn't get to talk about. It's related to the story of deconfined quantum criticality, and we had a pretty nice story understanding this intricate structure of the emergent symmetries from the duality story. Oh, I forgot to put in the reference here. This was collaboration with Adam Nahum, Max Malitsky, Chen Ke-Xu, and Sento 8 years ago. And then it's related to many other things like topological phases, quantum Hall effects. One future thing which has always been in my mind is, there is hope that we may use this ideas of dualities to understand something really difficult in condensed matter physics, which is quantum critical points with disorders. These are really difficult, but also very, very relevant to actual experiments. With that, let me just put the same summary of story here, and thank you for your attention.
Oh, okay. Thanks for being perfectly on time despite my slight interruption. So are there questions? More questions?
Yeah. Yeah. So the depending on how much you want me to say. Okay. Yeah. Okay. Okay. Oh. No, we don't have example like that. We don't have so when I say emergent symmetry, what I mean is something more conventional. It's just a case where in the UV both theories have a rather small symmetry, but the symmetries don't agree. And then in the IR, you should get some larger symmetry that at least contain both as subgroups. So that was used to understand some funny symmetries people have observed numerically in some quantum critical points between magnets. Yeah, so that's what I mean.
Okay. More questions? Yeah.
Is there any such duality in higher dimensional without supersymmetry?
It's a question that I've thought for a while, but no, I'm not aware. The thing, yeah, there are many ways to answer that question. First of all, it's much harder to get interesting massless theory in higher dimension anyway. Another curious fact is that if I try to generalize along this line, right, the real reason why you can generalize, you can go from 2D to 3D, is that in 2D, this Z2 has pi 0 non-trivial. In 3D, this U1 has pi 1 non-trivial. So the most naive thing you want to do is in 4D, you want something that has non-trivial pi 2.
Yes.
None of the Lie groups does that. So yeah.
Thank you.
Okay. We do have a little bit of time. Anybody? No? If so, let's thank Chong again for wonderful time.